In the last two modules, we built our architect's office. This is our FastAPI server. And we built our global logistics hub. This is our message broker. But there is a missing link here. The logistics hub doesn't actually make anything. It just routes boxes. If a user triggers an advanced AI agent, say, research the market, generate a 20-page PDF and email the board, our architect cannot do that at their desk. The server would freeze. Instead, the architect writes a precise blueprint, hands it to the logistics hub, and the hub delivers it to an offsite manufacturing plant. Tools like Celery in Python or MullMQ in Node are those offsite plants. They sit far outside your web server, running massive heavy machinery for minutes or hours at a time. To build enterprise-grade AI systems, you have to understand exactly what happens inside these factories. Let's break down the four mechanics. Mechanic number 1, task serialization. When your FastAPI application tells Celery to run a LangGraph agent, Python cannot send a live memory reference of that function across the network. The task must be serialized. It is stripped down into a flat universal text format like JSON. Because of this, your background workers must be completely self-sustained. You cannot pass an open database connection or a live OpenAI client to a worker. You only pass primitive instructions like a task ID and a user ID. The offsite plant has to read those raw instructions, boot up its own database connections, and fetch its own data. Mechanic number 2, the factory floor. Once the blueprint arrives at the plant, how the plant organizes its workers determines how much heavy AI processing your system can survive. You have two choices here. First, the Prefork pool. This spawns completely separate operating system processes. This is mandatory for CPU-bound AI tasks like running local Hugging Face tokenizers or calculating vector embeddings. Each process gets its own memory and completely bypasses the Python GIL. Second, the asynchronous pool. If your background worker's only job is calling the Anthropic's API 50 times in a row, you use this. It saves massive server memory by using productive waiting. So the worker finishes the 10-minute research loop. It generates a brilliant response. But remember, the worker is completely disconnected from the web server. Where does that data go? Mechanic number 3, the result backend. When the offsite factory finishes building the product, they don't ship it back to the architect's desk. They lock it in a secure warehouse vault, usually Redis or PostgreSQL, and assign it a unique tracking number. If your front-end UI needs to display the results, your FastAPI server just takes the tracking number, queries the vault and asks, is task 1, 2, 3 done yet? The vault replies with pending, started, or the final JSON payload. Mechanic number 4. And this is the one that saves your production app, the power failure protocol. In AI engineering, background tasks will fail. The OpenAI API will throw a rate limit. A vector database will timeout, or the network will glitch. If a worker crashes 80% of the way through a task, the message broker might assume it failed and hand the blueprint to a different worker to try again. Because of this, your tasks must be idempotent. That means running a task 5 times produces the exact same result as running it once. If your agent charges a credit card, you must write defensive code so a retired task doesn't double charge the user. And when you do retry, you use exponential backoff and jitter. If an AI API goes down, you don't immediately smash it with a retry 1 second later. You wait 2 seconds, then 4, then 8, and you add random milliseconds of noise, the jitter, to give the upstream AI services breathing room to recover. Let's look at the entire map. The architect, FastAPI, quickly accepts the user prompts and keeps the UI responsive. The logistics hub, RabbitMQ, holds the backlog of tasks safely during traffic spikes. The offsite plant, Celery, executes the long-running Landgraph loops outside of web memory. And the tracking vault, Redis, stores the final state for async retrieval. Master the pipeline and you can build an AI agent system that scales to millions of users. Now let's look at the production code that wires them together. We are going to walk through our shared contact, our worker setup, our tracking vault, and finally the exact terminal commands you need to control your factory floor. Let's open up the IDE. We begin in config.py. This is where both our web server and our background workers look to understand the rules of the system. Look at Celery configuration. We connect Celery to RabbitMQ as our broker and Redis as our result backend. But look at line 18, task underscore serializer equal to JSON. Remember, Python cannot pass a live object over a network to another server. It must serialize it into a flat universal string. To enforce the string format, we define our agent research payload using pedantic. Notice it requires a user ID and topic and an idempotency key. We convert this payload into a flat dictionary before sending it across the wire, ensuring our worker remains self-sustained. Now let's switch to task.py. This file runs exclusively inside our Offsite Manufacturing Plant. Look at the decorator flags on our run heavy research agent task. This is our power failure protocol. If an external LLM API throws a 503 rate limit, we don't crash. We use retry backoff equal to true and retry jitter equal to true. This forces Celery to back off exponentially, waiting 2 seconds, then 4, then 8, and injects random milliseconds of noise to prevent our workers from crashing the upstream AI providers. Next, look at how we enforce idempotency. Before running the expensive AI logic, our worker contacts a separate Redis instance and tries to set a unique lock key based on our tracking ID. If the lock already exists, it means another worker factory is already handling this job. The current worker instantly bypasses it. This line alone prevents you from double charging a user's credit card if a network glitch triggers an accidental task retry. With the worker ready, let's open main.py, our FastAPI architect. When a user triggers research, the API converts our pedantic model into a raw dictionary and runs apply async method. This drops the serialized payload onto the RabbitMQ conveyor belt and instantly returns an HTTP 202 status code along with a unique task ID. The user gets an immediate response while the heavy lifting happens elsewhere. But how do we check on the progress? Look at the status endpoint. We use Celery's async result to check our tracking vault, the Redis backend. If the tasks is pending, we tell the user it's in the logistics hub. If it's started, it's on the factory floor. And if it's success, the vault automatically safely unpacks the final JSON research report generated by our agent. To actually launch your offsite plans, you don't run Python scripts. You use the command line interface on your background servers. And your choice here completely dictates your application's performance. If your AI worker is running local CPU bound tasks like calculating matrix math, processing local vector embeddings, or running tokenizers, use the Prefork pool. This spawns entirely separate operating system processes, completely bypassing Python's global interpreter lock. So your cores can crunch numbers in parallel. However, if your background worker's only job is sitting around waiting for external network endpoints like OpenAI or Anthropic, switch the pool to Eventlet. This uses an asynchronous loop inside the worker, allowing a single server to handle hundreds of concurrent agent executions using almost zero RAM. So, serialize your data, enforce your idempotency locks, build your status vault, and pick the right concurrency pool. Master the distributed pipeline and your AI system will scale seamlessly. Do share this video if you think it would be useful for someone you know. Thanks for watching. See you in the next video.